So now we should go to the next our speaker. That is Sabine Reffert. She will tell about the Waltz Telescope and Spectrograph, searching for exoplanets around giant stars. So welcome, Sabine.
Yes, hello, good evening. My name is Sabine Reffert, and I work at the State Observatory at Heidelberg University in Germany. And what you see on the picture is our little Waltz telescope. It has a primary mirror of 72 centimeters. It saw first light in 1906, so that's quite a long time ago. And we've upgraded it considerably in the recent years, and I want to tell you how we did this. I will focus on the practical aspects, not so much on the science. Also, I will briefly touch on that also on my last slides. That works. So we have a pretty large team that has worked on the project over the last few years. First, there's a permanent staff, Andreas Quirrenbach, our director, who focuses also on the science. Julian Stürmer, who focuses on instrumentation. Myself, I come from the science side to this project. And then we have people from the mechanical and electronics workshop that we have at the State Observatory. On top of that, we have really a lot of students, one postdoc, a lot of PhD, bachelor.
So, excuse me, Sabine, we cannot see your full screen mode. So really? We don't see your slides.
Yeah, the slides are not advancing.
Okay, it was now. They are advancing on my screen. So I don't know.
No, still not.
Still not. So let me go back and change how I share.
We are seeing your first slide.
I see, yeah, that's strange because I see the second already. I'll just stop and share again in a different way. So. A moment, please, to change some options here. So now I start sharing again. And I'll go to full screen mode. Hopefully this works. You see the slides again?
Yes.
The first one, yeah, and now the second one?
Yeah.
Yes, perfect.
Okay, perfect. So sorry about that. So here you see all the names of our large team. I've gone through briefly already. There's no point in reading all of them. I just want to make the point here that it's really a lot of people, and in particular students, who have worked on this project during the recent years. So I go to the next slide. This is a picture of our observatory. You can see a lot of old telescopes, small ones, typically 50 to 80 centimeters in diameter. And none of them has been used for science recently. They have been used for science a lot when they were first built, but not in the recent years, not in the last 10 or 20 years at least. The site is not particularly good. It was a good site compared to what people did 100 years ago, but not now. Nowadays anymore. It's close to the city of Heidelberg, as you can see. It's only at an altitude of 570 meters, 450 meters above the city. And it has quite bad weather, lots of foggy and rainy nights, and it also has bad seeing. So that was our starting point. The other thing was that we had been carrying out a radial velocity survey to search for exoplanets around evolved stars, so giant stars, since 1999 already at Lick Observatory, where we also used a quite small telescope, 60 centimeters. And it was attached to this great high resolution spectrograph, the Hamilton, which was also used to detect some of the first exoplanets that were known via radial velocity. And yeah, we carried out this radial velocity surveys for 11 or 12 years until 2011, when the iodine cell broke at Lick Observatory. The iodine cell is used to provide a rather stable reference for the radial velocities because the iodine lines don't move. So taken all together, having this small telescope sitting around at our observatory here in Heidelberg, and no other telescope where we could continue carrying out our radial velocity survey, we decided to upgrade one of the small telescopes, the Waltz Telescope, with the required instrumentation to continue our RV survey of giant stars. And I'll detail the steps we had to go through for the upgrade in a minute. First, I want to make the point here that also the telescope is small and the site is bad. It's still worthwhile to take the steps and upgrade the telescopes for precise radial velocities, because for such a Doppler survey, there are lots of very, very bright potential targets. Our targets are all brighter than 6 magnitude, and there are thousands of those, so we can't monitor them all. There is still a lot of very bright stars that haven't been monitored for for exoplanets with the radial velocity method at this magnitude range. So that means a small telescope is perfectly fine, is sufficient for the task because we have bright targets. Furthermore, spectroscopy is largely insensitive to sky brightness and seeing, in particular, determining the radial velocity, where one measures the shift of the spectral lines. It's not so important that the sky is really dark. So the nearby city doesn't matter so much, and the seeing also doesn't matter so much. It only enters the equation. So it only enters via the throughput. So that means if the seeing is bad, we might have to observe a little longer to arrive at the same signal to noise of the observation in the end. But it's not limiting us in any way as it would be for imaging. For such a project, also the observing cadence and the number of nights that are available to the project is very important. So proprietary access is very favorable, as we have. Even for a site with bad weather, if you have a few good nights each month, it's worth the effort, I would say. And then finally, a high resolution spectrograph, an iodine cell, and a scientific grade CCD can be added with moderate amount of funding, but some funding, of course, is required. What is also very important to our project is the student participation. I said already that a lot of students have worked for their master, bachelor, and PhD projects even on this Waltz telescope and the survey that we intend to carry out. We will also, as soon as everything is ready to go, we will also involve other students in the scientific observing, and that's something the students really value. We had some nights already where some of them participated, and the feedback is really very good. They really like to get their hands on some instrumentation and do some observing early on in their studies. So here is just 2 images of the telescope. It's in a wooden dome. It's under monument protection. It is operated in NASMS focus, and it's an equatorial mount. The second floor hosts the telescope. And on the first floor, we have the spectrograph, which is fiber fed. And it sits in a separate room, and then the other stuff, electronic and computers, are also on the first floor of this dome. So now I go through the different parts that we added. The most important one is, of course, the spectrograph itself. We designed and built it ourselves with the help of some experts in the field. Some of them are at our own institute. So I'll briefly walk you through. I cannot see my own cursor now, so I cannot point it out, unfortunately, but you see where the fiber input is indicated on the top plot here or picture. That's where the light enters the spectrograph. It then goes to the collimator, goes to the shell grating, goes back to the collimator, finds an intermediate focus right on a very small mirror right next to the fiber input, then goes back to the collimator through the prism into the camera and the CCD at the very end. The resolution of the spectrograph is 61,000 as measured. It's most effective, has highest throughput in the, we cover the wavelength range from 4,500 to 7,000 angstrom, but the iodine region where most of the iodine lines are located, that's roughly between 5,000 and 6,000 angstrom. That's where the throughput is highest. So we have really optimized it to be used with an iodine cell. And the whole setup has been designed for an RV precision of better than 5 meters per second, fully sufficient for a precise ray velocity survey searching for exoplanets around giant stars, because the giant stars themselves show some radial velocity jitter. That's for the best targets around 5 to 10 meters per second. So there is no point to go to even better precision than this. And this is perfectly suitable for the iodine cell method. So then another part that we had to attach to the telescope is the front end. The front end takes the light as it comes from the telescope. And finally, at the end, the light is injected into the fiber that then leads to the spectrograph. The first element in the optical path there within the front end is a pickup mirror, which just receives the beam out as it comes out from the telescope and redirects it through our front end. Then the light goes through the iodine cell. You see the housing here, and both the pickup mirror and the iodine cell can be moved in and out of the light path with little motors. Then follows the guiding unit, which we have attached. Guiding works via a small pinhole mirror, or a mirror that has a small hole in it. And if all the light goes into the fiber or into the instrument, then one sees nothing. It's dark because none of the light is reflected off the mirror. But if the pointing is not perfect, then one sees some of the light as it's reflected off the mirror. So it's similar to what is usually referred to as slit guiding. And then we have a small guiding camera that looks at this mirror. And then finally, the fiber feeding unit that injects the light into the fiber to the spectrograph. Additional infrastructure that we needed to make everything work. The guiding system I mentioned already. In addition, we also have a photomultiplier installed that counts the photon as they enter our instrument. It registers the time when each photon basically enters, so that we can calculate the photon weighted midpoint of the observation, which is important for relatively long exposures to optimally correct for the barycentric motion of the Earth. And we use light from the zeroth order of the echelle grating of the spectrograph of the spectrum to count those photons. Then we have a calibration unit with various lamps, so an argon lamp, a lamp for flat fields, and an etalon. We can switch between those calibration sources via a fiber switcher. And then we have also a calibration fiber that runs from the calibration unit to the front end. and where we can eject calibration light instead of the telescope light into the front end. We do this so that the path that the calibration light and the telescope light goes through the instrument is largely identical. And then we had to automate a dome rotation that wasn't done automatically before, but has been upgraded so that the dome now follows to where the telescope is pointing. And we also had to automate the dome opening. This has not been fully done yet, but it will not prevent any observations soon, hopefully. We have acquired the parts to do this already with an electric winch and an inductive charging system that comes from electric cars. And then we, of course, we had a weather station and an all-sky camera installed so that we have access to the current weather as well. So then we have also written observing software. In the beginning, we tried to operate everything with commercially available software, but that did not work at all. It caused a lot of problems and delays, and it all started to come together much better once we had started to write our own observing software, which we could really tailor to our needs and the particular hardware that we have in our instruments, such as the photo multiplier, for instance, or our guiding system, which is a little bit special. So we have integrated this all in one big piece of software written in Python, and that's easy to update also if we want to do modifications in the future. We have also written already a data reduction software, a pipeline. You see a schematic of the WaltzDRS data reduction system. It uses two available Python packages, Ceres and BarriCore for basic extraction and calibration of the raw spectra, and BarriCore for the barycentric correction. The big part that we have added is iodine, which is a code to model the iodine spectra to finally extract the radial velocities. And this is really where all the logic sits, and that is most valuable, because up to now, no iodine code to extract precise radial velocities was available publicly. But iodine will eventually be published by Paul Heron. He is preparing the paper at the moment. He did not start from scratch. He started with a code that was developed by Rasmussen 2016 at Aarhus University for the Waltz Telescope, which also uses an iodine cell as reference for the radial velocities. And Paul Heron used this code and in collaboration with the people in Aarhus, developed it further to upgrade it and also to make it general enough so that it can work with different spectrographs, not only with one spectral format. So it works already for Lick and Song iodine spectra with quite good precision, and it will also work for the Waltz spectrograph eventually. The Song, in particular, the Waltz telescope can provide radial velocities with a precision of 1 meter per second, as using the Song internal pipeline from Aarhus, but this 1 meter precision can also be achieved with the Waltz, with the iodine code, basically here, as demonstrated already, and as will be shown in this paper by Paul. So skip one. So now I come a little bit to the science from our radial velocity survey at Lick Observatory that started 20 years ago, and where we have routinely monitored 386 G and K giant stars. We have published planets around 10 of the objects in the survey, more than 10 planets, because some of the objects Some of the giant stars harbor more than one planet, sometimes two. And on top of that, some of the detected discovered planets are in stellar binaries. So often these systems harbor really more than two components in total. I have just highlighted 2 of the 10 here. On the left, Iota Draconis, which was the first one. It's a rather massive planet in a 500 and something day orbit. And you see an additional linear trend on top of that. That's caused by another object in the system with a rather long period. And on the right, you see another object that is actually a spectroscopic binary, as you see by the large variation of the radial velocity of almost or more than 8 kilometers per second. And top of that, you see a small wiggle, which is due to a planet in that system. So I've just put this here to give you an impression of how a well-behaved radial velocity curve with a planet looks like. Because here on the next slide, I have put 2 other curves that might at first sight also make you think that there's a planet around, but actually, if you look closer, that's not the case for these 2 objects here. On the left side, it's Aldebaran. I haven't shown all velocities available. That's only ours from Lick. There's many more radial velocities available. And if you analyze the whole time series, you will see that the period is not consistent over time. So it cannot be a planet. You also see quite a lot of scatter around the fit that has been overplotted here. So that makes you maybe already suspicious, but it's relatively regular, just not over very long time scales. So one has to be really careful in interpreting radial velocity curves of giant stars. And on the right side, it's Epsilon Cygni. It's also a possible planet was a candidate planet in a spectroscopic binary. The spectroscopic binary orbit is very well known. It has a very long period, more than 50 years, I think, but it's nevertheless well determined. And then there is a small wiggle. Sorry. But when you analyze this, there's also a very long time series available. It's also not consistent over longer time scales. So that makes you wonder. There are other examples where almost periodic radial velocity curves cannot be interpreted as orbiting planets because the radial velocity variations correlate in some cases with H-alpha index or with other line shape parameters, and that tells you the variation in radial velocity that you see is really not due to a planet, but to some other phenomenon that's more intrinsic to the star itself. And what we want to find out with the survey that we are planning for our Waltz telescope is exactly what is behind these radial velocity variations that are not due to planets. What is the mechanism behind that, and how can we distinguish better between those objects that really harbor a planet and those that don't, which are the best parameters to look at. So this is why we want to continue our radial velocity survey, also because we want to confirm planets in much longer periods. We are nearing now 20 years or so as a time baseline for our survey, and it would be quite interesting to find some more planets with periods of the same order.
So thank you, Sabine, for your interesting presentation. So we see that this telescope is recovered and ready for the future work, and we probably can discuss, if you like, about including this telescope to our Europlanet telescope network. So now we do not have time for questions.